Alright, so in this video I'm gonna be explaining another important article with the title Graph Representation Learning via Aggregation Enhancement. This important paper in 2023. So the GNN have become powerful tool for processing graph structured data, but it still faces challenges in effectively aggregating and propagating information between layers, which limits their performance. We tackle this problem with kernel regression, using KR loss as primary loss in self-supervised setting or as a regularization term in supervised settings. We show substantial performance improvement, and as opposed to mutual information, this kernel regression loss is convex, so easy to estimate in high-dimensional cases, even though it indirectly maximizes the mutual information between its inputs. So there are three contributions. We provide evidence that KR loss minimization leads to mutual information maximization. And the convexity makes it a more practical alternative to mutual information. And then they show that KR-based regularization improves information aggregation. Then they develop a self-supervised graph representation learning named GIRL, which significantly outperforms previous state-of-the-art contrast-based algorithms. So Lee showed that the GCN model is a particular form of Laplacian smoothing and raised the concern of over-smoothing. GNNs have many problems, fundamental problems. I've listed 10 of them: over-smoothing, over-squashing, over-correlation, overfitting, lack of good positional encoder, natural, the locality problem. Then there are many other problems. So there are about 10 to 12 fundamental problems that I discovered after reading 300 papers on GNN. But over-squashing is even harder than over-smoothing. And some of them are the cause of other problems as well. So there is a causality structure between these fundamental problems of graph neural network. So you see this schematic representation of GIRL, where L of SSL, this one, is a sum of kernel regression losses between the graph G-in and graph output of each GNN layer. So by minimizing the KR loss between HI and HI from previous layer, we improve the information propagation and indirectly maximize the mutual information. This representation reminds me the paper of Jump as well, that we can take the readout from different layers and concatenate them, or take the max or LSTM or any other things. So a node attributed graph is a tuple where X are node features and E is set of edges, and the set of direct neighboring nodes of I is just neighbors of I. And the graph encoder F theta is parameterized by theta, and the node attributed graph and generated node representation. Finally, the classifier P phi, which has parameter phi, takes these embeddings as inputs and produces logits so that we can use this cross-entropy loss. The graph encoder G theta is composed of multiple GNN layers. And D is just the depth of the network. G theta L is an intermediate, this one is intermediate GNN layer. So the architecture is like this. And in B, it shows by minimizing the KR loss between the HI of L, the node representation of output graph, and Y sub I. We have node representation H and also the label Y. So what is the relationship between them? So in self-supervised setting, the goal is to learn a meaningful graph representation without access to node labels. To achieve this, a self-supervised algorithm is used to learn parameters of graph encoder. The quality of the learned representations is then evaluated by training a network for the downstream task, with the frozen extracted features as input and node labels as outputs. So you see a single intermediate GNN layer receives node features. So the mutual information approach is when mutual information between the representation and the label is zero, the random variables are statistically independent. So I, mutual information, is a measure of dependence of two random variables. But it's hard to approximate that. So any idea like this paper that tries to handle this problem more effectively is very important. That's why I have picked this important paper. So we can achieve this by maximization of this quantity. Mutual information in high-dimensional random vectors is hard, but they propose this kernel regression, which is easier to estimate and does not require additional learnable parameters. So they introduced this important variable, the distance between random variable y and the set C of x we want to evaluate. D is just the distance between two random variables. The important thing about this rho is in this theorem that says you can have an empirical estimate, and you see it's related to this one, and K here is just the X is a gram matrix. So this pi is just a projection into image of K, because K is a gram matrix. This is just a proof, but we can use it here. So now with the we can turn back to the graph supervised setting. We propose to replace the maximization of total mutual information by minimization. So this problem is very hard. As I said, we are trying to find a simple way to handle it. So this one is much simple. And we propose a self-supervised. So in the self-supervised setting, our goal is to transfer as much information as possible from the random variables h and z to the next layer. So we seek a we want to minimize the total distance. This is the total distance between the current node embedding and the previous. So it's enough to find this optimization problem. And you see for protein-protein interaction. By the way, you can use PyTorch geometric to access all of these data sets. For me, biomedical data sets are very important, like proteins, enzymes, DD data set. But those are for graph classification, but this one is for more about node classification. For example, different tissues, different protein graph, they interact, they have different functions. It's very important. State of the art is still not good. Still 85%. If we could rely on even this article. So the kernel regression achieves 80% for the protein-protein interaction, for the depths of 18 layers. Do you know you need 18 layers? And let's think about it. There are 18 layers and they don't have any pooling layer. Oh, I think they should use pooling, hierarchical pooling, because the computational complexity will be reduced significantly. So this is the Garrel algorithm. The trick is here that we want to minimize this loss. And just we apply stochastic gradient descent to this important loss.